Okay, let's start today's lecture on the transformer and associated codes. So, transformer models are so popular that there are probably 100 blogs, videos, etc. And in my Jupyter notebook, I have linked something which I cropped from a course in Amsterdam, which I like personally very much. So those blogs and professional tutorials will do much better job for introducing transformer and large language model to you than what I can do. My main goal here is to give you the concept of self-attention and how it first does a language to language translation, and I will come to the point where this language to language model, which is a sequence to sequence, can be generalized for any set to set mapping. And finally, I will try to give you an analogy where you will see this set to set mapping using scaled dot product attention, whatever that is, we will come in the lecture, that is equivalent to a message passing network. So that's why I have picked up this topic, that at the end of this lecture, we should be convinced that the transformers are some special form of graph neural networks. So why is that? That will be the end of the story. So let's start with what a sequence to sequence modeling is. Now you must be familiar at least that all this machine learning driven translation, or when you see text generation, etc., this neural network acting on human languages, uh, they are something called transformer. So what it's at the core is mapping a sequence to sequence. What does it mean? Think of the following. You want to write a function which will act as a translator when you're doing Google translation. And then you have a sequence of words as input, and your target is again a sequence of words. It's not just only few words randomly shuffled. The order of the words in a sentence matters to make a human meaning. So that's why in this list of the words, the positional encoding is a core essential feature to make it human interpretable. So essentially, the kind of neural network we are trying to do is that given some input sequence, a encoder kind of model will map it to a latent space, and then the latent space will be decoded by a decoder model, which will give you again some sequence of words or any other set of elements where the order in this set is an essential property. So this is, we are trying in general a global class of model where we are mapping a sequence to a sequence, a set to a set, but the order of the elements in this set is important. So we will try to see how that happens at the core. Okay, so there are this. So I have taken this video from a very nice blog by a person called Jay Alamar, and all of you should go, and I mean, it's linked in my notebook. That's one of the best blogs on transformer. One is that, and then there is another blog by the Harvard NLP group called Annotated Transformer. I strongly suggest you, all of you, go through that pages, which discusses the idea and gives you the illustration in much better way. Here I'm trying to give you just the core of it, how it works. So here you see that this is a language translation, and how it works. At each time step, the words get encoded into some latent space features in some hidden state. And then consecutively, the decoder takes each of the steps one by one and translates out the language. So the core feature of this is that there were sequences of words where the position of the words in a sentence mattered. The encoder mapped it to some latent space, and the decoder again tried to understand the correlation between variables and produced an output set with the right ordering. Now, it's not necessary that the set size here has to be same as the set size here. Like there can be additional prepositions and verbs here, but the right meaning should be translated when you're translating, like this example was given in French to English translation. So there are difference in the total number of words used in the input sentence versus the output sentence, but the correlation among the latent space features were learned by the neural network so that it can predict the right language. Let's take this example once more again, like in a real life transformer encoder and decoder, there are stacks of several encoders and several decoders. So just let's try to visualize how the latent space feature propagation happens. Okay, so here you see that each of the words are sequentially processed by some encoder. You have all the latent space together, and then the decoder learns the correlation among these latent space representations and finally gives you a correct output. So the whole point of this sets of model in general is that you have an input set, you have an output, you have a target output set. There is a positional correlation between the elements of the input set which needs to be learned, and the latent space should encode that information, and then the decoder should sequentially decode the messages to give you the right output set. Okay, so these are the kind of models which we are interested in when we look into transformer. And now we will try to learn that what goes into this individual blocks and how do you build them up. So right now it's just a figure. I didn't tell you how, given a sequence of set elements, how to actually code it up and put it inside an encoder, how to form the latent space, and how to run the decoder. So this was solved in 2017 in a paper which named Attention is All That You Need, which proposed this architecture. And I don't know, by now probably this paper has 20,000 citations, something like that. I mean, let's say a few order of magnitudes higher than what physics papers get cited. But the whole point of this part is that the green blocks which you were seeing in the previous element, they are built by something called multi-head attention. What is that stuff? We will discuss. But for the time being, you see that this part is the encoder block and this part is the decoder block. What goes here is a embedded layer. Like if you have some elements in a sequence, you find some say an embedded like some latent dimension representation, and then you also enforce the neural network to carry the information of the positional encoding of those set elements. They are fed to a neural network block. How to build that we will discuss soon. And then this has been passed to a decoder block which uses similar kind of attention mechanism and gives you the output. So the whole network is built on several attention blocks. Okay, so that really is the bare bone fundamental part of this whole architecture, that attention mechanism really computes the cross correlation among the elements and is successful to predict the output sequences. So now we will see how to build that thing up. Okay. So is the problem clear what we are trying to do? We have a input set we want to predict an output set, but the order of the elements in this set is important. That's what the natural language problem is in the sequence. And we want to understand this right correlation among the ordering so that we make right predictions. Okay, so that's the thing we are trying to do. So this notebook, the top part should link you to the YouTube and the actual repository from where I have taken it. I have cropped a part of that and added stuff of my own, but you should go and see these repositories. They're fantastic, much more professional than what I can do in my finite ability. But I followed them, so I really would like to ask you to do it. Okay, so first, let's see. This is the diagram which I just showed you. What does attention means? Okay, so let's go to the attention block diagram. Shall I put it this way? No, let's do the following. Let's say those elements in the sequence had some feature because that was a set, and each set has some features. So let's call them X. You have a bunch of elements, and for each of them there was X2, Xn. Those were the features sitting on the elements of the sets. Now, I showed you there is an embedding layer, and what does that do? It creates a latent space representation, and then for each element, it creates 3 pieces of tensor for each of them. One is called query, one is called key, and one is called value. So for each of the embedding, you create through a neural network 3 pieces of data: query, key, and value. And how you can do that? If you have, let's say, a neural network, say theta of q, let's say, and that acts on x to create the q vector. Similarly, key is some neural network acting on x, giving you the k vector. Similarly for v. Okay, so these are learned representations for each set elements, and each set element has a value: query, key, value. Then, yeah. Different network without weight sharing. Good question. There is no weight sharing among. Yeah, so it's a different network. That's what I mean, that there is no weight sharing. Okay. So if it was like one big multi-layer perceptron and the output is one part is called Q and other part was K, that would have been called weight shared outputs. But these are independent blocks of, in general, multi-layered perceptrons. Okay. And once you do that, then you try to combine the query, key, and value vectors to create attention scores. So the attention score between the elements, something like alpha ij, if you take a pair, that should be some sort of function of qi kj vi, the way it's constructed. We will see what is that function is, and there are variation of that functions. But given this representation created for each set elements, you try to create an attention score. And the output is, sorry, here I told you something wrong. It's my mistake. The attention score is Qj. And the final output of a single attention layer you form by multiplying the output of the ith element is alpha ij vj summed over j. So you combine the information by creating some attention score and then multiply by the value to get the total output. Okay, so we will see how to code that up now in this. Oops. Yeah. Yeah. Right, right, right. Uh, so they didn't explicitly, so they summed over the key. So I didn't write it, the query for each element. I mean, they didn't write the query for each element as well, but in general, you can write it as separate parts and we will see how it's done. Okay. So set elements, one is ith element and jth element. And for each of the element, you have 3 pieces of tensors. And you're picking up a pair, computing some attention between the pair, and then on a target set element, you're doing an aggregated output. Right? So I'm trying to give you the overall mathematical concept which is used. And you can read this notebook as well, and you should read the, yeah. It's a special case where you can intentionally create in that way, but it's not, it needn't be true in general. If you want, you can keep it generalized like this. Okay.
Is this attention that we are calculating, alpha ij, is something like the correlation between these three?
Correlation between a pair.
Huh.
But now we will see that that function f, what was proposed in 2017 paper is this thing. It's called scaled dot product attention. Okay. So what does this formula means? That Q, if there are n elements, and Q is some latent feature vector of some D1 dimension, and K was another latent representation of similar dimension, n times D, then you can do a matrix multiplication. But since it's a transpose, n cross D, and transpose gives you D cross n, so this piece becomes an n cross n matrix. Okay, so this is a matrix multiplication. And then you multiply by another column vector of size n. And that is the attention score for all the vectors taken q, k, v. And why it's called scaled, you just normalize this dot product by the square root of the dimension. So that's why called scale dot product attention, this formula. But it's nothing very complicated. It's just you had created these vectors, and they are in general for n elements, n cross some hyperparameter dimension matrix, and you just do a matrix multiplication here. And finally, they proposed an activation function of softmax on the output of the dot product. Okay, but this is how they computed. So if you think of a diagram, you take Q and K and do the matrix multiplication. So QK transpose. The scale part is 1 by square root dk. So this masking was optional, which is not appearing in this formula. You apply a softmax, and whatever is the output of that, you again do another multiplication, like matrix multiplication with the latent feature vector V. So can you associate this formula with this diagram? Okay, so this is what is called scaled dot product attention score. This is how you compute. Now, there is another concept we need to discuss called multi-head at. Okay, first of all, given that's the scale dot product, there is a code snippet how to compute it. If you are given 3 tensors Q, K, and V, you can see you are doing a matrix multiplication, QK transpose. This division is what is doing the 1 by square root descaling. And then finally you apply the softmax, which is the activation. And again, you do another piece of matrix multiplication with the V. So very 5 lines of function implements the scale dot product attention. And you can play with this, like you can play with putting arbitrary tensor shapes and just try to understand how the scale dot product attention is computed. Okay. Now we need to go to a concept called multi-headed attention. So let's look into this picture. Previously, it was one single attention process which was computed. Now, what we will do, we will try to perform this single piece of feed-forward operation multiple times in parallel. So we will start with query, keys, and value. And then this particular operation will happen multiple times. So what will come out of this? If this whole stack is computed, say, 6 times, then you have in parallel 6 output vectors and things like that for each of this stacked parallel head. And finally, you just concat them. You just stack them up and pass it through a linear layer, and that's the output of multi-headed attention. So how do we formulate that? Use just like the previous way, you compute for the ith head the single attention score. And once you can compute the single attention score for the ith head, you can just stack them up. And by now, you should be pro of concatenating tensors if you're dealing with the notebooks. You know through which dimension the tensors have to be concatenated. You merge them, and this W0 represents this linear layer. So after concatenation, you pass it through another linear layer, which is essentially like a matrix multiplication. And this is the output of the multi-head attention. Are you with me? How the computational flow to start from some feature vectors, building some query key value representation, and finally pass it through some parallel attention head, and finally getting the output of the multi-headed attention. Oh, so this stuff is think of as a single attention head, and you are doing this in parallel. And then you're taking the parallel output, merging them together, and passing through a linear layer to get the final multi-headed attention output. So this is what this diagram means. Even there the multiple layers like that. Right. So here Wi are the weight parameters of a single layer. You see some stacked picture here. Wi is a weight parameter associated to one single scalar dot product attention layer. And then let's say you have 5 or 6 of them. Then for each of this stack, you have a different weight parameters. You process the output. For each of them, you will get a different output. And you club them together and then pass it through the linear layer, which is this weight parameter W0. And that's the definition of multi-headed attention output. Uh, Not one value, it's for the whole set, because we are doing it on the whole set. No, wait, this, this is not, this was value for each element. Okay, so think of Q, K, and V are some vector which consists for each element. And then for each element, this thing is happening. So finally, you have a multi-headed attention score for the whole set. Yeah, yeah. So it's all happening on the whole set. Which one? Oh, H is the number of heads, which was, I was telling, 5 or 6 heads. Okay, so how many of these stacks are put in parallel? That's the number of heads. That's an hyperparameter of this network. Number of layers in this parallel diagram. That H is an integer. How many such parallel layers stacked there? No, weights are not a priori decided. That's you train on. Yeah, so the weights are upgraded through backpropagation, where all these weight parameters are updated simultaneously, right? Good. So now let's go through the code of how a multi-headed attention is implemented. So what will be your input? Like there should be an input dimension of the tensor, the embedding dimension, and number of heads. That should practically finalize. Okay, the picture is gone, but what will be the dimension of the tensor which is coming in? What is the dimension of the tensor which you want to be after the whole output? And how many number of heads you are using for the stack? So those goes as the parameters of this neural network block. For simplicity, you can see that the weights are initialized by some Xavier uniform random number. But here, one piece of neural network was doing that QKV creation, and another piece of neural network was doing the final output. After the stacking, it was passed through a WO, which is given by this O projection. And the rest of the piece of code is essentially, we just showed you a function how to compute self-attention. That has been repeated here. And then you do a scale dot product attention to get the attention score for the heads in parallel. You club them all together and finally give output through that projection layer with weight parameters WO. So you should be able to match that picture with this piece of code. I mean, that's something I like to do, that when you visualize a layer, how the feed forward operation is happening versus how it's coded up. I mean, of course, you have to run the codes yourself and see how the tensor shapes are getting modified. But at least from the visual point of view, you should be able to see how it has been done. Okay. Sorry? Yeah. when you created this QKV from X, they needn't be same dimension because it's a learned representation created from the X through a neural network. So the dimension has been changed, and that the dimension of QKV will be the embedding dimensions. Not like some representation. Those are vectors which are function of trainable parameters. No, you're not by hand assigning a value. You pass it through some MLP or something and create a latent representation V. I can't hear you. Wait, the mic is coming.
Okay. You showed that function there, that input dimension, is that equal to that xn there in?
Yes. And there was an embedding dimension.
So we have to by hand put the dimension. So how
Yeah.
a word it is linked to that dimension, means a
So,
sentence can be um, composed of many words. So
you remember when we are doing some linear layer or even MLPs, we are specifying some input dimension and some output dimension. That's something you are specifying by hand. Now, if a tensor comes in with the input dimension as the last dimension, after passing through that layer, it will become the same number of elements times the output dimension,
yeah, okay.
right?
Yeah.
So here it's also some input dimension and the embedding dimension of this query key and values.
Okay. So okay, it will train itself and
Yes,
okay.
because these are uh, learned representations of the feature tensor. Yeah, yeah. Not necessarily. You can control it. Rather, you really want it to be a little different so that when you stack these layers, few multi-head attention layer, it goes to some higher dimension, comes down lower, and you can control what will be the output dimension as you specify the parameters of the hyperparameters of the network. No, I just said in general, it's the feature of the elements of a set. Think of that way. Yeah. The x's will be the words. No, I mean, it's just a variable set size. So you can just, if required for making a mini batch, you can probably zero pad at the end, but the network will only work on the non-zero elements. But in general, it's a set to set problem, and these sets can have variable sizes. Okay. Number of heads. So in order, if you compute, do the algebra, what makes sure that given some parallel heads, the output dimension and the input dimension are, if you divide by the number of heads, it has to be an integer, right? Otherwise, it doesn't make any sense. So that's the constraint which has been written in that language. No, no, no. So when you see the way it was written, all the parallel heads were just copies of each other, which have different uncorrelated weight parameters, but the dimension of the tensors has to be Otherwise, you can't stack them. Right. And it's the tensor shape were same, otherwise you couldn't have stacked them together. That you have to keep track of. It's just independent copies. That's the multi-head. Yeah.
So number of heads should be less than, less than the embedding dimension, right? Less than or equal to.
Sorry, okay.
The number of heads,
Yeah.
the multiple heads, they should be less than the dimension.
Why?
Like the, as you said, it should be 0 modulo.
No, think of this, that you have few different independent heads, and then you have dimension of the input tensor QKV, and then you have bunch of outputs. If you can control a single operation from QKV to output I, then this is just replicated for each parallel head. Now, how many heads you want to put? This operation is independent. Like you put one head, the forward computation is happening. You put another head, another independent parallel forward computation is happening. So you can just stack them up.
Okay.
Yeah.
Hello. So for every element, we have H independent heads in set. For every element in a set,
Right.
we have H independent heads.
Then you
So we are
summed over that, when you do the concatenation, you again summed over the dimension of H.
so our input goes like a sequence.
This input, no, when it's multi-head, that goes as parallel. And the sequence matter when you compute the self-attention for the each element. So each forward computation through one head takes into account the sequence of the elements. Okay, but the order of head, that is that can be changed. Like there is no meaning on the head 1 versus head 2 order. The ordering all comes in the sequence of the input set. So let's say the tensors have some dimensions, I don't know, whatever, and finally one head gives you a dimension 1. Okay, so if you have h heads, after concatenating the same tensor, we'll have the other ones untouched, h, and then you stack up and sum over the dimension of h. So in principle, you're free to leave that as dimension h, or you can try to sum over. But when you see this concatenation, you just stack over the dimension, and if you have this h floating, then you design that W0, the last layer, the head, the last linear layer, that W0 should contain this parameter h as a number, so that it can map the output into your desired dimension. Right? So you can leave it without summing, but then you have to take into account the final W0 in such a WO in such a way that the elements of when the matrix multiplication happens, it happens along that h dimension. Yeah, but then probably you lose information, because what's the point of making these parallel heads if you are not using that information?
So purpose of this projection is to associate the weight matrices to these QK.
You have independent weight elements which are processing the same QKV.
Uh-huh.
Okay. Right? Great. It's I think it's just making the network deep enough without losing the sequence correlation. If you had, instead of going parallel, if you made it sequential, these heads, you would have lost the correlation, the positional encoding which is coming. That's why they're going parallel instead of sequential.
Or can we say that different heads pay attention to different stuff, and at the end you
No,
take?
I don't think so. I mean, since this is all happening in a latent feature,
Yeah.
you can't make that kind of concrete statement. But the whole point is not.
Yeah, suppose I had just one layer.
Yeah, the
Okay.
single
thing. It paid attention to something based on whatever training I did. But I'm putting two heads. The weight matrices in between are different, right?
weight matrices are
So
different
that means
and
they are learning
uncorrelated.
different stuff.
I don't know how to interpret this because I don't have an explainable model for this. But just when you make it parallel, you still retain the sequential.
That for
yeah,
sure.
Yeah, that's all it is.
That's all. Okay.
Yeah, I mean, I can't make a statement like different heads are learning different correlation or things like that. I can't make a statement like that.
I was trying to draw something similar, parallels between what we have multiple layers in CNN, because they do learn different stuff, and then when we do the convolution, they again kind of add up.
I'm not sure if that similar analogy can be drawn here.
Yeah, if the algebra is same, then perhaps yes, but that's my understanding.
Yeah, but here you don't. Sorry? Right, but not in the scalar dot product attention.
Okay.
Okay. No, so it's the same kind of correlation, but now you're making the network deeper. But if you had put several heads one after another, you will lose the correlation among the input sequence. So you don't want to lose that. That's why you're putting the heads in parallel. Okay. Good. I like this. The rest is like I have put the whole piece of code how to write a multi-headed attention. And if you look in the transformer paper, the picture we showed you, the picture was at top. Okay, so there is a layer normalization. What I was discussing is all about this yellowish box of multi-headed attention. And then there is a layer normalization, and the feed-forward network is just a simple linear kind of layer, so which we will discuss. Okay, so we had a feed-forward network, which you can see there is a max filter and two linear pieces, W1 and W2. And layer norm, what does it do? It converts x to x minus mu by sigma. That's it. I mean, if you look into the source code, it just mu of x by sigma of x plus there is a regulator epsilon so that this thing doesn't blows up. That's what the layer normalization does. So if you're given x as an input, the first formula lets you compute the feed forward network outputs. It's just some linear layer and bias. And the second one, layer normalization, just converts the tensor into a normalized one. Okay, so the encoder block was all about a multi-headed attention and this feed-forward network. So if you stack these two one after another, you have built the encoder part of the transformer. And similarly, the decoder part was similar, a construction of same multi-headed attention and feed-forward network. So the whole encoder was some pieces of this network, and similarly the decoder. The encoder encodes whole information, the positional encoding into some latent space, and the decoder decodes. Okay. So once you have these pieces of individual codes together, you can wrap it under an NN dot module, and you can see that the encoder block has a multi-headed attention, and then there are a bunch of layer normalization. So one multi-headed attention and 2 pieces of layer normalization. That was the encoder block. So let's go to this formula. So one multi-headed attention, and here is one layer normalization, and here was another piece of layer normalization. You can exactly see that same thing in the encoder. There is a attention, multi-headed attention, and then normalization. Okay. And then you can code up the decoder as well, similar way. Now, in the first paper, they used a positional encoding. What they demonstrated is by some sine and cosine function that they allocated the positions. So what does it mean? Is that in this big picture, this positional encoding, what went into on top of the embeddings are some sines and cosine positions for the set elements. So we have this is not something very deep, so that I need to explain. So the positional encoding stuff just creates for each element some positions which are sines and cosines, and that what goes into the encoder block. Okay, so so here you can see a pattern of the sines and cosines which are coming back for each hidden dimensions which you created for the embedding. And this was just a plot which was first given in the same paper, just to understand how the positional encoding was used for the training of the transformer. But these days researches are going on for different positional encoding as well. And yeah. So this is the encoder, which takes a QKV kind of representation, input embeddings, and the, yeah. So this goes in, and then in the multi-headed attention of the QKV, one part is coming from the embeddings of the output and 2 part is coming from the encoder. So this is how the information from the encoder is fed to the decoder. Sorry? So Q and K are coming from the encoder, and the V is coming from the embedding of the decoder itself. Here. Okay. Right. So if you just read the source code, I mean, here, standing here, it's no point for me to read the source code, but given the code, you should be able to associate the flow lines of that diagram, which part has been taken from the encoder block and fed to the decoder block. Right? Okay. And you can see the positional encodings, etc. And they use some cosine learning rate to do the training, which I'm not going to do it anyway here. Okay. I just kept it because they showed in the data set how to do the training of this transformer, but I don't have hardware memory here to do a large training, and I tried to download a data set, but here it was so slow. So I won't go into the training here. What is now important for me is to come to this part. So why at all I took this when the first few lectures were all GNNs. Now here you try to see that when we are doing language model, there is a positional order, and all these cross arrows are learning some mutual correlations. That was the self-attention score. And this can be thought of a set with some ordered connection, which is by definition is a graph. Okay, so there has to be something that given a positionally encoded set, when you learn the self-attention score, which by construction, the alpha ij I wrote, that looked similar to the edge weights, learned edge weights, what we have discussed for the last 2 days. So let's try to see how that analogy goes in. First, let's see the attention score. Okay, QKV. Now, if you think of the following, in a graph where you have a fully connected graph for that set, then for each node, and you have a full connection, whatever way you want to do, you have 3 pieces of node data: QI, KI, VI. Okay. Now, if you're, remember that was a matrix multiplication, QK transpose. Okay. So the ijth element of that matrix should be something like alpha ij, sitting as the learned age data. So if you can spread, if you try to draw an analogy of the sequence of elements with a graph and try to draw a message passing kind of analogy, then QIKJ transpose should be equal to the created messages. And once you take the aggregation of it and multiply by V, that should be analog to the node update. So the first part of the attention score, QK transpose, should be equal to the message, and then multiplying by V should be equal to the node upgrade. And with a sum pooling, because it was matrix multiplication anyway. So creating the self-attention score is essentially one instance of a message passing network, which we learned. Edge feature is not used here. That's why the psi is only dependent on, I'm just giving a trying to analogy. There were 2 pieces of node data, Q and K. On every node, you take the Qth data from one node and Kth data from another node, stack it together, pass it, and create the age data, Mij, which is Qi Kj transpose. And then when you aggregated it and did another matrix multiplication to multiply by the V, that is essentially the node update. Right? So now, this was a special case where we drawn an analogy that the scale dot product attention can be thought of as one instance of message passing network. But the flexibility you gain by redrawing this picture is that now you are not bound anymore to give the message only some special format of QK transpose by square root of T. You can combine Q and K with your favorite desired function and create a new message function which should solve your purpose. So this entire set-to-set problem with a particular sequence can be generalized to a message passing network. And that's why the whole transformer network is a special case of the generalized message passing network category, where the messages can be identified as a self-attention score. Is it clear from this picture? Right? So now we will see some extensions of this method that once people realize this, they try to propose transformer networks on general set kind of data and also graph like transformer based convolution on the graph. So how that is done, that will follow from here. But what is called originally what was called transformer is essentially a special case of a message passing network, and this is the point I wanted to reach out of this discussion. Okay. Now think of any set-to-set problem. For any set-to-set problem which has this mutual positional encoding, you pass it through an encoder, get the output through a decoder, you can write it on as a message passing networks. Okay, so let me just go through it. So the first part will be point transformer convolution. We want to implement this network where the attention score here is now this quantity alpha ij, which is a softmax acting on this quantity. So we have total 4 pieces of network here, W1, W2, W3, and the delta ij itself comes from output of a network H theta. So unless, I mean, without writing the code, can you visualize that this can be implemented as a message passing network where the middle line is the created messages and the top line is the node aggregation output? How many of you are not following? No, Ritesh, not you, I'm asking others. Does this make sense? That now you can start doing research and developing your own attention scores and try to see whether it's serving your purpose better or not. Given the physics problem in your hand, you can define your attention scores and try to see the performance. Right? So let's now just code this up. That given a set, a point cloud, you can apply this stuff, and let's see how it goes. So let's see what are the neural network. So you will pass an attention network, which will create the attention scores, and the W1, W2, W3 are just linear layers. Okay. And then you see it's just a message passing network where you define the message as this softmax of the created attentions, alpha. So delta was there in the definition, which was position I minus position j, and was passed through a neural network. So this is this line. And the alpha definition, alpha ij, was alpha I minus alpha j plus delta ij, where each of these alphas were computed out of W1 and W2. Right, so, and yesterday only you learned that the messages are created within this message function in the PyTorch geometric framework. So that's what has been used. And you have implemented your attention mechanism. Yeah. W1 and W3 are learned matrices, like the weight parameters of the network. No. So let's go through the formula. How many W's you want? You want, just like you are creating Q and K from different nodes in this analogy, you see W1 and W2, one acts on I, another acts on J, right? And then it combines the positional encoding, which is through this neural network H theta. So it combines the attention scores with the positional encoding. And the final update is done through W3. So 3 steps. Right? So exactly what we were doing in the canonical transformer. There were encoded positions, and also you have this Q, K, and V, and we combine everything to make a scale dot product attention and then gave a output. We just repeating the same thing with individual bunch of uncorrelated neural networks, but we just implemented it as a message passing network. Right? Great. Then I want to go through another piece of code, which is like a bit more advanced version of the softmax, and you created what is called GAT convolution. So we will try to implement this H score that the H is formed out of there is one theta and theta E, which are the neural networks, and there is a bunch of leaky ReLU. So the H scores are normalized by the aggregated sum from all the edge. So it's a normalized H score, okay? And then it's just an update, a node aggregation. So leaky ReLU, you guys know, right? What is, who doesn't know leaky ReLU? Oh, many of them. What is ReLU? So ReLU is one-way filter, and leaky ReLU, given the slope, also takes into account the negative part. Okay, and you can, in the leaky ReLU, you can give this, how much it will be passed in the negative side is a parameter of leaky ReLU. So it's just a filter, nothing else. Just nonlinear activation. So otherwise, you see again theta xi and xk, and you can, and in this formula you can also input some age attribute which can be taken into account for creating the attention scores. You have the EIJs, right? And the rest is just how to implement this message passing network. So again, in the forward function, you calculate the source and destinations, the xi and xj, after passing through all the neural network layers. I mean, I can't, there's no point in reading this code, but you can just see how the, okay, one important thing, which the reason why I included this definition, this example, is that yesterday when we were doing graph nets, the meta layer, you saw there was an age update layer, a node update layer, and a global update layer. But when in the first instance, when I was talking about the message passing layer in PyTorch geometric, I didn't show you what is an age update layer analogy. It was all like existing age information and club the node information, create the messages, and aggregated the messages. But there was no scope of introducing this at the first go, but message passing layer also has an age update function, which exactly equal to the phi e, the age update network which we talked for the meta layer. So whatever we did as meta layer yesterday can also be translated into message passing in the PyTorch geometric context and vice versa. So those are just general concepts, and you can implement any way you like to do. So there is an inbuilt edge function in the message passing class as well, which can be used to first create the updated edge representation, and those updated edge representation can be used for creating the messages when you create the message function. So that psi, xi, xj, and the edge function can be updated edge function, where E prime will be created from E through this edge update function. Okay. So, so this is the way you can design your attention scores and implement them as message passing networks. I can't hear you. Yeah, yeah. No, I mean, I just uploaded it in the day 3. Huh? Yeah, day 3 folder. I mean, this is the code which was uploaded. I don't know. I mean, that shouldn't, because I didn't touch this code after I uploaded. So maybe I can re-upload once more. I don't know. Okay, okay. So do you see this piece of code in your computer? Gatconf. Okay, so I don't have any more material to discuss for this lecture. So what I wanted to show you what is scale dot product attention, how the transformer network is built, how it is one-to-one synonymous and a special case of a general message passing network. And then I tried to show you, you can design your own attention function and write down as message functions. So this is probably in the last day I can try to show you how the particle transformer in the context of particle physics is built, which is to give you a concrete example how these things are implemented in context of particle physics. But this is what I had to tell you overall, that transformers are special cases of graph neural networks. So if you have question, go through the piece of code. Since we have some time, probably 15 minutes odd, we will be happy to discuss it together. Oh, that was in the diagram, no? So you go. So look at this big famous diagram. So it's here where the output of the encoder is going to the decoder.
These images are not coming in the.
Sorry?
These images
are not coming because you have to upload it. I think.
Oh, right, right. I forgot to put the image from my computer to the GitHub. I will do it.
And that PDF file, few pages PDF file.
Yeah, sure. Right. I mean, it should be smoothly differentiable and apply the layer norm for keeping the overall normalization within check. If you satisfy these two criteria, more or less that's a valid function.
I'm just thinking, since mostly things are either the linear functions or the non-linear. So
Yeah,
these are
MLP.
well behaved.
Yeah, I mean, if you write an MLP, which is a universal approximator of a nonlinear function, and you know how MLP behaves.
Yeah, so then
Yeah.
these are well behaved.
Yeah. I mean, and only case where it can do some nonsense is the layer normalization, but it already come with a regularization parameter. So epsilon, so that you avoid zero division kind of things.
Is a controllable parameter?
Yes, you can. That's a parameter which is.
Kind of hypo.
I mean, you can put what value you want. Okay. 0.1 or 0.001, you can put it. Okay. Hmm?
It will be regulated. If I
Yeah.
0.1, nothing will go more than 10.
Yeah. Okay. So maybe you just try the codes a little bit and see if you have question. At least the scale dot product attention function. There is an example snippet code how x is converted to q, k, and v, and how the attention scores are computed. Sorry?
For transformer, looking for HEP example. That you did in the last year.
Just you can apply the, so on any set data, you can apply a transformer. So the kind of problems you were doing, like either jet, and now jet is a set, you can do a set to set mapping, a set to vector mapping, anything you like. So these are universal approximator, like universal functions on sets. And you can, and particle physics problems, the input data is often a set.
Another question would be like, here the sequence matter, but in set sequence doesn't usually. So what kind of sequence one is looking for in the, say, one crude example will be good enough?
I don't know if you think of a particle decay chain as a set.
Or the shower.
A shower. Yeah. I mean, there the sequence matters. Yes. The physics is meaningful there, the order. And if you want to do machine learning on those kind of data, this will be useful. Tree is an ordered set, right? I mean, yeah, the branches. Sorry? Yeah, so if you really want to embed that sequence, you have to design something analogous to positional encoder of your own externally. And you have to feed that.
Can be encoded into positional.
Hmm?
If I have a tree and can encode into positional something, that's all I want.
Right. Right, it's a general set-to-set mapping. What? I mean, set to vector. Right, right.
So, hello. Yeah. So basically, it's something called transductive and inductive learning. So transformer, when you use for this NLP, which he just described right now, that's basically a transductive learning where you have two fixed things and you just want a very nice map between these. The data never changes. Language is there, language does not change, right? No. Only one paragraph, it's not the things. The full set of spoken language of, say, English and the full set of spoken language of, say, French. Those two things are already always fixed, right? But you want to translate the English language to the French language nicely. You want to map English to French in a very efficient manner, right? So that is where the NLP transformers are used for. But for us, more likely, we don't have the data set fixed. We have generated data and we want to train it on the simulated data, but we want to apply it to some unknown data, but we assume that it always follows the same distribution that we have sampled. So these two are essentially two different things.